Hello, well wishers, critics. How are you today? It's Professor Suresh. Delighted to be back again for my 13th video to be published on YouTube. And the topic for discussion today is composite materials, a boon or bane. What do you think, guys? Okay, I'll start with the basics. Today is what? May 12th, 2020. Okay, a composite material, or also known as composition material or shortened as composites, is a material made from two or more constituent materials with a significantly different physical properties that when combined produce a material with characteristics different from the individual components. The individual components remain separate and distinct within the finished structure, differentiating composites from mixer and solid solutions. It's again Wikipedia definition. Well-known examples of composites are lignocellulose, simply straw, STRAW, in sludge. 2. Wood, cellulose fibers embedded in hemicellulose and the binder lignin. 3. Bones, soft protein, collagen combined with a hard mineral apatite. 4. Perlite, ferrite combined with a cementite. Classification occurs at two different levels. 1. First criterion is based on the matrix, the binder constituent. The main composite families encompass organic matrix composites, shortly OMC, metal matrix composites, MMC, and ceramic matrix composites, CMC. Term OMC generally refers to two classes of composites. They are polymer matrix composites, shortly PMC, and carbon matrix composites, CMC, which are usually called carbon-carbon composites. 2. Second criterion refers to the reinforcement phases. Here, fiber reinforced composites, FRC, laminar composites, or particular composites are distinguished. FRC can be further separated into those containing discontinuous or continuous fibers respectively as reinforcements. FRC consists of fibers surrounded by matrix materials. Laminar composites consist of material layers stacked together by the matrix. Particulate composites constitute particles distributed or embedded in a binding matrix. The particles can be in the form of flakes or in powder form. MMCs, metal matrix composites, are generally low cost but have a relatively high specific mass. Proper material selection for an envisaged application is crucial in development of the new product. Applications are infinite. Composite materials are a major growth area within advanced materials and reached sales of US $21.2 billion in 2014. The top three market segments in 2014 were transportation, construction, pipes, and tanks. Other segments include energy, automotive, and aerospace. Cellulose fibers, due to their abundance and mechanical properties, are among the most important resources for the development of bio-based composite materials. More recently, cellulose nanofibers like nanofibrillated cellulose NFC and bacterial cellulose BC, NFC and BC gained particular attention in this context because of their unique features and properties. NFC is obtained by disintegration of common plant fibers using high pressure homogenizers and has a high aspect ratio and specific surface area combined with a remarkable strength and flexibility, low thermal expansion, high optical transparency, and specific barrier properties. BC is produced by several bacteria has a tri-dimensional network of nano and microfibrils and has high purity, water holding capacity, crystallinity, tensile strength, and Young's modulus than conventional plant fibers. Impact damage characterization of composite structures is a huge field of research due to the vulnerability of such materials to transversal loads and the complex failure modes involved. The final part properties of a composite material are dependent on the material's characteristics and part fabrication process. Materials used in aerospace industries should have high strength to weight ratio, corrosion resistance, and high fatigue resistance. A composite material, as I said before, is a combination of two or more materials with different properties that results in better properties than those of the individual components used alone. In contrast to metallic alloys, so each material retains its separate chemical, physical, and mechanical properties. The two constituents are reinforcement and a matrix. The main advantages of composite materials are their high strength and stiffness combined with a low density when compared with the bulk materials, allowing for a weight reduction in the finished product. That is basically it will have a high strength to weight ratio, light. The reinforcing phase provides a strength and stiffness. In most cases, the reinforcement is harder, stronger, and stiffer than the matrix. The reinforcement is usually a fiber or a particulate. Particulate composites have dimensions that are approximately equal in all directions, unidirectional. They may be spherical, platelets, or any other regular or irregular geometry. Particulate composites tend to be much weaker and less stiff than continuous fiber composites, but they are usually much less expensive. There is a saying in English, you cannot have the cake as well as eat it. Okay, so if you want a better material, one has to spend more money normally. Particulate reinforced composites usually contain less reinforcement, up to 40 or 50 by volume percentage due to processing difficulties and brittleness. A fiber has a length that is much greater than its diameter. The length to diameter, L by D ratio, is normally known as the aspect ratio and can vary greatly. Continuous fibers have long aspect ratios while discontinuous fibers have short aspect ratios. Continuous fiber materials normally have a preferred orientations, while discontinuous fibers generally have a random orientation. Examples of continuous reinforcements include unidirectional, woven cloth, and helical winding. Examples of discontinuous reinforcements are chopped fibers and random mat. Continuous fiber composites are often made into laminates by stacking single sheets of continuous fibers in different orientations to obtain the desired strength and stiffness properties with fiber volumes as high as 60 to 70%. The continuous phase is the matrix, which is a polymer, metal, or ceramic. Polymers have low strength and stiffness. Metals have intermediate strength and stiffness but high ductility, and ceramics have high strength and stiffness but are brittle. The type and quantity of the reinforcement determines the final properties. Composite materials can be classified as either isotropic or anisotropic. Isotropic materials have the same material properties in all directions, and normal loads create only normal strains. By comparison, anisotropic materials have different material properties in all directions at a particular point in the body. There are no material planes of symmetry, and normal loads create both normal strains and shear strains. A material is isotropic if the properties are independent of direction within the material. Bulk materials such as metals and polymers are normally treated as isotropic materials, while composites are treated as anisotropic. Okay. When there is a single ply or a layup in which all of the layers of plies are stacked in the same orientation, the layup is called as a lamina, Lamina. When the piles are stacked at various angles, the layup is called a laminate. Laminate. Continuous fiber composites are normally laminated materials in which the individual layers, plies, or laminae are oriented in directions that will enhance the strength, particularly in the primary load direction. The advantages of composite are many. I already mentioned so many. Okay, including lighter weight, that is higher strength to weight ratio, the ability to tailor the layup for optimum strength and stiffness that we can control in fabrication, improved fatigue life, higher corrosion resistance, and with a good design practice, reduced assembly costs due to fewer detailed parts and fasteners. Composites to occur in nature, example in tree trunks, spider webs, and mollusk shells. A tree is a good example of a natural composite consisting of cellulose, the fibrous materials, and lignin, a natural polymer forming the woody cell walls and the cementing reinforcement material between them. Bone is also another good example of a natural composite. Most of the things that exist in nature only are replicated in some way, that is called as bionics. In one other lecture I mentioned that. Okay. The bone salt plates made of calcium and phosphate ions reinforce soft collagen. Historically, they have used various composites right from Stone Age. Plywood by Egyptians in 1500 BC, strengthening of mud bricks with straw or bamboo shoots in rural areas, medieval swords and armor with layers of different metals, that was in 1800 AD, glass fibers reinforced resins in boats and aircrafts in the 1930s. FRPs, fiber reinforced plastic. Okay, long fibers in various forms are inherently much stiffer and stronger than the same in bulk form. In fibers, the crystals are aligned with the fiber axis. Moreover, there are fewer internal defects in fibers than in bulk material. Nowadays, composites are used widely for surgical implants, sports equipment like tennis rackets, sports bikes, cycles, defense, bulletproof vests, ropes and cables made with Kevlar 29, spectacle frames. Okay. Kevlar, trade name aramid fiber, is an aromatic compound made of carbon, hydrogen, oxygen, and nitrogen. I presume by this time all of you have a basic knowledge of composites and potential for various applications in real life. Okay. After watching this video, to summarize, I would say mechanical engineers can develop composites for appropriate optimal applications. We'll meet again real soon. Rest in peace and harmony. As I have suggested before, always watch these videos with a closed caption or subtitles for enhanced comprehension. I know I rushed through to complete the presentation within 20 minutes maximum so that you don't feel bored. Take care.